Let's integrate using partial fractions. Recognize that the denominator has an irreducible quadratic factor that has been repeated. That's what makes this case 4. To begin with, I'm going to temporarily ignore the integral and focus on just the partial fractions. The first fraction, we're going to put the x in the denominator. So the numerator is simply just a. The second fraction will have x squared plus 1 in the denominator. Since it's quadratic, the numerator will be bx plus c. The third fraction will be dx plus e, divided by x squared plus 1 quantity squared. At this point, we want to multiply both sides by the LCD. That is x times x squared plus 1 quantity squared. Again, we are ignoring the integration for just a moment, just focusing on fractions. On the left, the LCD times the fraction will cancel the denominator, leaving us with 5x to the fourth plus 7x squared plus x plus 2. Then on the right side, if we distribute the LCD with the first fraction, the x will cancel, leaving us with a times x squared plus 1 squared. And then we'll distribute the LCD with the second fraction. In that case, one of the x squared plus 1 factors will cancel, leaving us with bx plus c times x squared plus 1. Distributing the LCD with the final fraction, we'll get dx plus e times x. Now we want to clean all of this up so that we can eventually equate coefficients. For now, we'll just copy the left side of the equation. And now multiply a times, we'll need to square the binomial. That will give us a x to the fourth plus 2ax squared plus a. Then distribute bx with x and x squared. That is bx to the fourth. Distribute bx with x and 1. Bx squared. Distribute c with x and x squared. Cx cubed. Distribute the c with the x and the 1. Cx. And finally, we'll distribute the x inside the last set of parentheses. Dx squared plus ex. Now we can start to equate the coefficients. Let's look at all the coefficients that have x to the fourth. We have a x to the fourth and b x to the fourth. Focusing on the coefficients, that would be a plus b. And that's going to be equal to the coefficient of x to the fourth on the left side, 5. Then we'll focus on all the x cubed coefficients. On the right side, the only x cubed I see is c. It's going to be equal to the coefficient of x cubed on the left side. Notice we don't see x cubed, so the coefficient there is simply 0. So we got c right away. Now x squared. The x squared terms, we have 2a and b. And we have d. Those are equal to the coefficient of x squared on the left, 7. Then we'll go for the x terms. We have cx plus ex, so c plus e is equal to the coefficient of x on the left, which is 1. We know that c is 0, so that tells us right away that e must be 1. And then let's look at the constants. On the right side, we have a, and that's the only constant. It's going to be equal to the constant on the left, which is 2. So we know the value for a now. Using this info, we can now find b. A is 2, so b must be 3. And if we know everything else, we can now find d. A is 2, so we'll have 2 times 2 is 4, plus b is 3 is 7. Subtract 7 on both sides, d must be 0. Using all of this, we can now rewrite the original integral. To save time, I'm going to call the original integral I. I is equal to a, which is 2, divided by x, plus b, x, c is 0, divided by x squared plus 1, plus the last integral, d is 0, e is 1, divided by x squared plus 1 quantity squared, dx. Finally, we can begin the process of integration. The first integral is relatively straightforward. The integral of 2 divided by x is 2 natural log absolute value x. I'll save the plus c for the very end. The second integral is also going to be a natural log, but it may not be quite as obvious. So let's let u be x squared. Then du is 2x dx. I don't see 2 in the original integral, so let's divide by 2. 1/2 du equals x dx. Rewriting that integral, we now have the integral of 3 divided by u is x squared, so that's u plus 1 du, and we have 1/2 out front. Integrating this now, we have 3/2 natural log absolute value of u plus 1, which in this case is x squared plus 1. And again, plus c we'll save for the very end. The final integral is a little bit trickier. It's going to require some work. Notice that we have a variable squared plus a constant squared. If we think of that as 1 squared, this is going to eventually be a trig substitution. Let's let x be tangent theta. Then dx will be secant squared theta d theta. The integral will then be, in the denominator we have tangent squared theta plus 1 quantity squared, and dx we are replacing with secant squared theta d theta. Recognize that in the denominator we have an identity. Tangent squared theta plus 1 is secant squared. So the numerator is still secant squared theta. Again, in the denominator we are replacing this with secant squared. We have secant squared quantity squared, which makes this secant to the 4th theta, d theta. This is now the integral of 1 divided by secant squared theta d theta, which is the integral of cosine squared theta d theta. We don't have a rule to directly integrate cosine squared, but we can rewrite it using an identity that is 1/2 times 1 plus cosine up to theta d theta. We can then break this integral into 2 different integrals. We'll distribute that 1/2. We'll get the integral of 1/2 plus the integral of 1/2 cosine of 2 theta d theta. Forgot my d theta on that first integral. So the integral of 1/2 d theta is simply 1/2 theta. Here we again need a substitution. Let's let u be 2 theta. du is then 2 d theta. Divide by 2 on both sides. So this is the integral. I'll pull 1/2 out front. Integral of 1/2 cosine u du. We now have 1/4. The integral of cosine is sine of u, which we said is 2 theta. All of that is eventually plus c. So let me bring down what we had from earlier so I don't lose it. At this point, we eventually want to go back to the triangle and the fact that we said x equals tangent theta. But the problem with this last piece is we have a double angle. So let's again rewrite it in a manner that we can focus on just theta. Sine of 2 theta is 2 times sine theta cosine theta. Lots of trig identities here. Now going to the triangle. Let's call this angle theta opposite over adjacent. Then the hypotenuse would have to be the square root of x squared plus 1. We have 2 ln absolute value of x plus 3/2 ln absolute value x squared plus 1. Now looking at 1/2 theta. 1/2 is just a constant, so we can pull it out. And think of theta. If we needed to solve this equation for theta, we'll take the arctan of both sides, which means we'll get the arctangent of x, or inverse tangent x. And then dealing with the last piece, we can distribute the 1/4 with the 2. That will give us 1/2 sine of theta. Going to the triangle, sine is opposite over hypotenuse. That is x divided by the square root of x squared plus 1 times the cosine of theta, which is adjacent over hypotenuse. That is 1 divided by the square root of x squared plus 1. Finally, that last little piece we can simplify a tiny bit. We'll have natural log absolute value of x plus 3/2 absolute value x squared plus 1 plus 1/2 inverse tangent x plus x divided by 2 times x squared plus 1 plus c.